When you think of organic, what do you think of? You might think of a way of farming that uses biological pest control and is free of synthetic fertilizers. But when we talk about organic in chemistry, we're talking about a very specific branch of chemistry that focuses on carbon and hydrogen. Sometimes we'll have a few other trace elements sprinkled in like oxygen, nitrogen, phosphorus, and sulfur, but the main focus of organic chemistry is carbon. The reason for this is because carbon can make long chains, and carbon likes to share electrons in order to fill its octet. It likes to form 4 bonds. The way that carbon bonds is almost exclusively covalently. So there are a few inorganic carbon-containing compounds, and those are the ones that have ionic bonding, like carbonate and a few others. However, carbon prefers to share electrons, and when it shares electrons, it forms 4 covalent bonds. So this can be any combination. It can be 4 single bonds, it could be 2 double bonds, it could be 1 double bond and 2 single bonds, or it can be a triple bond and a single bond. But when carbon likes 4 bonds. It is also unique in the fact that it can form almost limitless chains of carbon atoms bonded together. They can be in straight chains, or they can be branched or form rings. And because of this, it allows many, many, many different compounds to be made out of carbon. And we can adjust its properties to what we want based on how it's bonded together. So carbon bonding does like to form 4 bonds. Here's some examples. Now I do want to share with you naming. So when we're talking about carbon naming, if there is 1 carbon, the prefix is meth. If there are 2 carbons, the prefix is eth. 3 carbons is prop. 4 carbons is bute. 5 carbons is pent. And then it continues on using the prefixes we've already learned for our bonding with two covalent elements. Hex, hept, oct, and so on. The other unique thing about naming for carbon is the ending. If it ends in ane, that means that it is strictly single bonds. If it ends in ene, then there's at least 1 double bond. And if it ends in yne, then there is at least 1 triple bond. And so we can learn a lot about the compound by looking at its name. So let's look at our first example here. We have ethene. So eth means that there's 2 carbons, 1, 2, and ene means that there's a double bond to our carbons. So this helps us decide that ethene has 2 carbons with a double bond. If we look at our next example, we have eth, which is 2 carbons, 1, 2, and the yne tells us that there's a triple bond between them. You can decide how many hydrogen there are based on the name because we know that carbon likes to form 4 bonds. So any bonds that are not to carbon are going to be hydrogen. If we have the word iso, iso means that it's branched, so there's a carbon coming off of another carbon. In this case, there are 4 bute, isobute, means there's 4 carbons with a branch, and the ANE means that it's all singly bonded. So isobutane, it's all singly bonded with a branch coming off of it. If it says cyclo, that means that we've formed a circle. Now I do want to explain something a little bit further, and this is what we call line angle drawing. So organic chemists, because they draw carbon over and over and over, they've come up with a method to draw the bonds. Because of the carbon always being there, instead of drawing carbons, they just draw lines. And it's line angle because any end of the line or any bend in the line is a carbon. So our ethene would be drawn just as 2 lines representing the double bond. We would know at the end of each of the lines, there would be carbon, and anything that's not drawn, any bonds that are not drawn, are occupied by hydrogen. If we were going to draw ethyne, it would just be 3 parallel lines representing the triple bond. Okay, so let's look at something like propane. Propane is all single bonds. Now we have more than 2, so it's not just the ends of the lines. But now we have to draw a bend. So propane would be a line followed by a bend and another line. This would be showing us 3 carbons. Anywhere where there's not a bond drawn, it would be hydrogens coming off of it. Now the reason that I show you this is because this is the vast majority of the way that compounds are drawn. And so for you to understand what these structures look like, you have to understand line angle structures. So let's look at isobutane. Isobutane has 3 carbons that are in the line, and then we have 1 carbon as the branch. So our isobutane would have that branched carbon coming off the second one in the line. If we look at acetic acid, so now we've added in some oxygen, and we do have to draw the oxygen in the structure. So we would have 1 line with a double bond to our oxygen, and then an OH. The H does need to be drawn if it is not attached to a carbon. Here, we would know that there are no hydrogens on the carbon with the double bonded oxygen because it contains 4 bonds, a double and 2 singles. So no hydrogen can be bonded to that carbon. If we look at cyclohexane, now it just becomes a hexagon when we draw our structure. And we would know that there's 2 hydrogen coming off of each of the points of our hexagon because there are only 2 bonds drawn. We can classify organic compounds a little bit further. We know they contain carbon, but if they are strictly carbon and hydrogen, no other elements, we call those hydrocarbons. Hydrocarbons are used quite frequently for fuels. So these are highly studied molecules because of their application to fueling our country. Contain mostly carbon and hydrogen. If we have other elements present, then they become functionalized hydrocarbons. And these would have oxygen, nitrogen, phosphorus, sulfur. But if it's strictly hydrogen and carbon, it's what we call a hydrocarbon. So some of our hydrocarbons include methane, which is the primary component in natural gas. So the Bunsen burners you use in lab run off of mostly methane. Propane you'll find in LP tanks, so liquid propane, that's for your gas grills, or if you live in the country, if you have a propane tank, that is liquid propane that is used to heat your house. We've got N-butane. N-butane is in like cigarette lighters or handheld lighters is butane. And 1 through 4 carbons are gases at room temperature. So these are all gases. But you might say, well, but my butane lighter is liquid. Well, that's because it's under just a little bit of pressure, and that pressure forces it into the liquid state. Pentane and larger, those are liquids at room temperature. Pentane, again, is 5 carbons. The N in front means that it's a straight chain, no branching. If we wanted to see these in line angle, our propane we've seen. If we do butane, we have to add another bend to our line. And if we do pentane, we have to add another line representing our carbons. So we would have 1, 2, 3, 4, 5 carbons for pentane. Ethene. Now, ethene has 2 carbons. This is the gas that ripens your fruit. So if you've ever put fruit in a paper bag or watched bananas ripen over time, that's because they're exposed or producing ethene in order to ripen them. Ethine, this is a fuel that's used for torches, for cutting torches, and it's also known as acetylene. What if we wanted to draw pentene with an E-N-E? Well, pentene, we would still draw our 5 carbons, and then somewhere in there, and if we don't have additional information, it could go anywhere, we would have to draw a double bond. If it was 2-pentene, that means that the double bond would be on the 2nd carbon. Functionalized hydrocarbons. These are, again, organic compounds that now have other elements in them. Typically oxygen, but we can also have nitrogen, sulfur, and phosphorus. So one of the most common functionalized hydrocarbons that you might be familiar with is ethanol. So ethanol is the alcohol that you drink in fermented beverages. Ethanol is 2 carbons long, eth. The AN represents the fact that there are all single bonds, and the OL ending tells us that it is an alcohol. Now, please note that this OH is not a hydroxide. It is bonded to the carbon, and we know this because they're all nonmetals. So this OH will not dissociate. It is attached to that carbon. Ethers are another, and now we have the oxygen between 2 carbons. So the R in our formulas are representing carbon chains. The R prime means that it may be different from the R. Ethers are used for anesthetic. They're also quite useful as laboratory solvents. We have aldehydes, where we've got a carbon double bonded to an oxygen with a hydrogen. These are quite fragrant molecules. so they get used in perfumes and flavorings quite frequently. Ketones are a double bonded carbon between two other carbons. One frequent ketone that you may know of is acetone, and this is fingernail polish remover. We also use it in the lab to help dry water because its boiling point is significantly lower than water's boiling point. Carboxylic acids we will see quite frequently. So alcohols and carboxylic acids are going to be the ones that we deal most frequently with in general chemistry. Carboxylic acids are carbon double bonded to an oxygen with an OH group on the end. And this is one whole group. So it is not an alcohol plus something. This is a carboxylic acid. And one frequent or common carboxylic acid is acetic acid or vinegar. The reason that this is an acid is because this hydrogen dissociates, like we've talked about with the other acids. And we'll talk about further in later chapters. Esters, carbon double bonded to an oxygen with an oxygen between carbon groups. And these are quite frequently laboratory solvents. And amines have nitrogen with two hydrogens attached to it. And these quite frequently smell like rotting fish. This is also part of the amino acids. So in amino acids, we have an amine group, and we also have a carboxylic acid group to make our amino acid. So here's an example for you. This is an insecticide that can get used on corn crops. Which functional groups can you spot? Pause the video and identify the functional groups. Which functional groups did you spot? Well, we have an alkene, which is carbon double bonded to carbon. So, like the ending says ENE, to represent that we've got a double bond, we call that an alkene. If it's an alkane, then it's all single bonds. If it's an alkyne, then there's a triple bond between carbons. We have an ester, which is carbon double bonded to an oxygen, bonded to another oxygen. We have a nitrile, which is carbon triple bonded to nitrogen. So you may not have known what the name of that one was, but that's a nitrile. And we have an ether, which is an oxygen between two carbons. So a few functional groups in this particular insecticide. So hopefully through this chapter you've learned quite a bit. If you want to test your knowledge and see that you have what you've learned, there are some problems that you can try at the end of the chapter. Odd number problems, the answers are in the back of the book.